Okay, today we are looking at the first lesson of our Unit 1, Tools of Geometry. This first lesson deals with inductive reasoning and conjecture, or patterns. So going through our notes, if you need a copy of these notes, you can always go to the Edmodo page and print off a copy of those, but you should have a copy of these. So first thing we're looking at here is we're going to look at, oops, sorry about that. We're going to be looking at inductive reasoning and what it uses. It uses specific examples to arrive at a conclusion. A conjecture, what that is we're looking at uneducated guess. For example, if I was to tell you that it is cloudy outside, and the street is wet, what might you say about that? What might your conjecture be? Well, you might say that it rained. That would be an educated guess, would be that it rained. A counterexample, an example that proves the conjecture false, would be if I was to say, okay, a counterexample would be the grass is not wet. If the grass was not wet, that would really disprove my conjecture that it rained. Now, I don't know what would happen to make that be the case, but whatever my counterexample would be to prove that my conjecture was not true would be, again, a counterexample. Okay, and looking at our next question here, we're going to write a conjecture that describes the pattern 2, 4, 12, 48, 240. Then use our conjecture to find the item in the next sequence. Well, what you're probably doing is you're looking at it and saying, well, 2 times 2 equals 4. Well, then we start with 4, and I know that 4 times 3 equals 12. 12 times 4 equals 240. So what we're doing here is we're taking each number and multiplying it by one more than the previous number. We end up with this. So if that was my pattern, or that was my conjecture, then to find the next term in the sequence, I would say that would make 240 times what number comes after 4? 5 would equal 1,200. So using my conjecture, I came up with the next pattern in this sequence. And looking at my next question, make a conjecture about the sum of an odd number and an even number. List some examples that support your conjecture. Conjecture. I have a hard time talking. So let's look at an example of that. Here's an even number. 2 plus an odd number would be 3. That equals 5. 13 plus 12, there's an odd and an even number, equals 25. 6 is my even number and 17 is my odd number. That equals 23. If I was making a conjecture based on these examples, I would say that the sum will always be odd, won't they? Each of these terms is odd. So I would say the sum of an odd number and an even number will always be odd. Now, unless someone came up with a counterexample, which I don't think you would be able to, that is a true statement. Let's look at our next example. ACE is a right triangle with AC equaling CE. We're going to draw a figure that would illustrate the following conjecture. So let's look at our examples here and come up with something that would so that we can draw a triangle. First of all, it's a right triangle, and it has points ACE. ACE is isosceles, so here we're going to make it right. It's isosceles, so this side would have to be equal to this side. Angle C is a right angle. That would mean this would be angle C. AE is the hypotenuse, so we would say that A and E is the hypotenuse. So we have triangle ACE with AC equaling CE, and we do have that right here. AC is it's isosceles, so that side is equal to that side. I know it's not drawn to scale, but that would be the case there. Find a counterexample to show that the following conjecture is false. So if I have AB equal to BC, that would mean that AB is equal to BC. If AB equals BC, then B is the midpoint of segment AC. Well, everything seems to be correct here, right? We look at that and say yes. Can we come up with a counterexample that says that if AB is still equal to BC, is there a way that B is not the midpoint of segment AC? Well, if we look at an example like our triangle, we can see that this is A, this is B, this is A, and this is C. AB, actually, no, I take that back. Let me erase that. AB is equal to BC. We would have to have B as my, let's try that again. So we have A, B, and BC. These two segments can still be equal to each other, but is B the midpoint of segment AC? That would be the midpoint. That is not B. So we have found a counterexample that shows that this conjecture, if AB is equal to BC, then B is the midpoint. We found a counterexample of that conjecture. Okay, moving on with the note. And here we have conditional statements. A hypothesis, the phrase following the if of a conditional statement, and the conclusion, the phrase following then in a conditional statement. That's the difference between the hypothesis and the conclusion. Determine the truth value of each conditional statement. If false, give a counterexample. So let's look at this first example. Notice that we have the if right here. If you subtract a whole number, so this is the hypothesis, since we have that if statement. If you subtract a whole number from another whole number, again, hypothesis, then, that should say then, the result is a whole number. This is the conclusion. Is that true? If you subtract a whole number from another whole number, is the result always a whole number? Well, I can think of a counterexample to that. If I have 2 minus 7, that's going to equal negative 5, not a whole number. So that is a false statement. The second one, again, if this is my hypothesis, if last month was February, then this month is March. Conjecture, or I'm sorry, conclusion. Is that a true statement? If last month was February, then this month is March. Can you think of any example where this month is not March? I cannot. Therefore, we would say that if the hypothesis and the conclusion is true, then the conditional statement is true. Again, the hypothesis and the conclusion have to be true in order for the conditional statement to be true. Okay, let's look at this little table that we have down here. Conditional statement, we represent that with symbols. P is going to represent my hypothesis, and Q is going to represent my conclusion. If we're going to come up with the converse statement, then we flip that and we put that original conditional statement's conclusion first, and we test that to the hypothesis. Is the converse always true? No, the converse is not always true when dealing with a conditional statement. Okay, looking at more of this table. A negation of a statement is the opposite. It has the opposite meaning as well as an opposite truth value. And we write that and we read that. We write that with this symbol, but we read that as not P. We wouldn't say squiggly P. We would say not P and not Q. Is the inverse of a statement always true? No. And the contrapositive is where we start with the original statement's conclusion. We would say not Q and not P. And this is important here. If the conditional statement is true, the contrapositive is true. That means if this original statement was true, then our contrapositive is also going to be true. And if the conditional statement is false, if we're starting with a false statement, then our contrapositive is also going to be false. So let's look at an example of how we would look at different conditional statements, converse, inverse, and contrapositive. Okay, so we have the original statement, the conditional statement, if the measure of an angle is between 0 and 90 degrees, then, so this is my hypothesis, this is my conclusion. The converse, remember, if you remember up above, we said that the converse starts with the original statement's conclusion. So we would then say if, because all of these will start with if, and we're talking about the measure of an angle, so we're going to include that here. I know that looks like it's in the hypothesis, but that's what we're talking about. If the measure of an angle, and now this is where we change it to the conclusion, starting with the Q. If the measure of an angle is acute, then this is where we put the conditional statement's hypothesis. Then the measure is between 0 and 90. And 90 degrees. Is this a true statement? Well, if the measure of an angle, or if the angle is acute, then the measure is between 0 and 90. That is a true statement. I can't think of an example where that would not be true. Is our original statement true? I forgot to test that. If the measure of an angle is between 0 and 90, then the angle is acute. Again, that is a true statement as well. Now I'm just going to slide down here a little bit and write my inverse below. Remember, I'll leave it here so we can still see my notes on inverse. Inverse starts with the negation of our hypothesis. So here I'm going to write my inverse here. I'll just do this. I'm going to start with, and I really shouldn't have started with the measure, if the measure, again, we're doing the inverse now, so I'm going to do the negation of my hypothesis. If the measure of an angle is, how do I write the negation? Not between 0 and 90 degrees. Now here's where I write the negation. Remember, my negation of my conclusion. Then the angle is not, that makes that conclusion, the negation, is not acute. Is that a true statement? Well, if the measure of an angle is not between 0 and 90, then the angle is not acute. That is a true statement. All right, and the last one, the contrapositive, without even doing this, we can probably tell that it's going to be a true statement because we saw here that the contrapositive, if the conditional is true, the contrapositive is true. So let's go ahead and start on this. The contrapositive starts with the negation of the original conclusion, which would be the negation of this conclusion right here. If the angle, how do we make that conclusion negate it? If the angle is not acute, then we write the negation of the hypothesis. Then the measure of an angle is not, making it a negation, between 0 and 90 degrees. Okay? And if the angle is not acute, then the measure of an angle is not between 0 and 90. That is a true statement. Hopefully these notes aren't too confusing and mixed up. There's a lot of writing today. If it was confusing, pause it, rewind it, whatever you need to do to have it help you make sense. Hope this helps. This is it for this lesson. Our next lesson we'll be looking at biconditional statements. So that's it for this one.